let's talk about electric dipoles. Who cares about electric dipoles? Well, let me show you what they are, and maybe you'll start to care. Here's a plus charge, and here's a minus charge. And they're separated by a distance d. And this is the electric dipole. Let's check it out.
You said it's a slow ride, everything's gonna be alright. All I gotta do is just hold tight, everything's gonna be fine.
Hello folks, welcome to the next lecture of Electromagnetism. Today we're talking about electric dipoles. I'm going to explain every single thing you need to know about dipoles step by step. We're going to be talking about the force on a dipole, the torque on a dipole, the electric potential energy of a dipole, how dipoles work, the applications of dipoles, why dipoles are important, how dipoles are calculated, and finally how dipoles are connected to electric potential. So let's get started. Alright folks, so let's start with the electric monopole moment. But what does that even mean? Well, let's start with the basics. And of course, if we have any questions at all, we have an audience member here, which is actually non-human, which will ask questions.
Hey!
So let's get started with the electric monopole moment. All we need to do is start with a charge. So let's say we have a charge, and that charge is, in fact, without even starting with plus 5q, let's just say it's a positive charge. Okay. What does the electric field for a positive charge look like?
Doesn't it point outwards?
That's correct. The electric field lines for a positive charge are radially outwards, like this.
That's the only thing I remember from electricity.
And that's the only thing you need to know.
Protons are selfless, electrons are selfish.
So we have a positive charge and its electric field lines are radially outwards. What about a negative charge?
Radially inwards?
Radially inwards, that's correct. So all of it looks exactly like this, but all the field lines are pointing inwards instead of outwards. Isn't that wonderful?
No, it isn't.
Now, a plus charge and a minus charge, do opposite charges attract or repel? Student?
I think they attract.
I think they attract too. And do like charges attract or repel, like a positive and a positive?
I don't think so. I think they repel.
They repel. So like charges repel, opposite charges attract. When you have a plus and a minus charge, they're going to attract, and the field lines are going to look like this.
Oh,
so
wow.
You just imagine that I drew it. So just imagine that you're connecting. See, that's how the field lines for an electric dipole looks like.
Oh, that's a really cool way of imagining it.
Yep. This is why it's called, this right here, a plus charge and a minus charge is all a dipole is. That's why it's called a dipole. Di, because there's two charges, plus and minus, and poles because they're of opposite polarity. One is plus, one is minus.
What
yes,
happens
question.
to those rays that are over
Good
there?
question. So the rays that seem to go outwards will eventually, if you zoom out, loop back and connect. So all of the rays will actually loop back and connect like this.
Wait, that's so strange.
It is really strange, and we're actually going to see that in a simulation shortly. But before we start talking about the dipole moment, we have to talk about the monopole moment. But what is an electric monopole? Let's check it out. So let's say we have a plus charge, but this time I'm not just going to make it a plus charge. I'm going to be extra bold. I'm going to make it a plus 5 charge. Okay? So you can imagine
Wait, why is Q there? Wouldn't you write Q equals plus 5?
No, you can write it however you want. This just means that if I had one charge, I would just put Q here, plus Q. But here I have 5 positive charges, hence plus 5Q. Now, if I had just one positive charge, I would have, what would my electric field lines look like?
Just outward?
That's right, radially outwards. But if I have plus 5 positive charge, how do you think my electric field lines would change?
they would be the same, but they would be like stronger outwards.
Stronger. And how can I represent them being stronger? Well, I
Longer
can just
arrows.
not longer arrows. We would just draw 5 times as many.
Oh.
I'm not going to draw all of them, but there you go. So you'd have like 20 arrows, for example, right? So here is a +5 charge. Now let's put a -3 charge right here.
Okay.
Okay, so as we know, the electric field lines for a negative charge look what?
They are inwards.
Inwards, right? Radially
So
inwards.
you could draw like 6 from this one.
Yeah, sure. So 3, 4, 5, 6. Anyway, so this is a +5 charge and a -3 charge, right? So imagine that the +5 charge throws out 10 lines of 10 field lines for every plus charge. So if it throws out 10 field lines for one positive charge, how many field lines would it throw out for 5 positive charges?
50. That's
50.
a really good way to algebraically represent.
And what about for -3? How many field lines would be thrown out?
-30.
-30. Now imagine that. Now just connect these field lines, and what you would see, what you'd realize, let me draw one over here. What you'd realize is out of the 50 outgoing field lines, how many are captured by the negative charge?
Only 30.
Only 30.
So
So
where do the other 20 go?
the other 20 now are no longer going to be captured. The other 20, they're going to head out to space, infinity. They're going to go out to infinity.
Is that how the monopole was created?
And that is, this is the electric monopole moment. Electric monopole moment.
So basically, the electric dipole is when two
Equal charges.
are in a relation, and then an electric monopole is when there is one bigger charge.
That's right. So in this electric monopole moment, the whole idea
Wait.
Yes,
I
question.
have a question. What if there was a bigger negative charge? Then those field lines
Let's try it.
wouldn't be.
Let's switch them up. So let's make it -5q and +3q. So how many is it gonna throw out?
Well, it's going to throw out
30 field lines, right?
Yeah, 30.
And how many will get captured?
30.
Well,
All
30, or you can think, hey, now the analogy starts to break down about capturing and stuff. But we can still draw a picture. Let's draw a picture again for this situation. Now the field lines are going to be switched around, right?
Yeah.
So which one is going to be throwing out charge? I mean electric field lines.
The positive one.
The positive charge. So and how many field lines will it throw out?
30. And all 30 of those are going to get captured.
Okay.
But then 20 of the field lines that the electron has will be single.
Right. So you're going to have, for example, something like this. I'm not drawing everything, obviously. And this here, since it's a negative charge, it's going to be radially inwards. So connect them up. All the field lines from the positive guy are going to get captured, right?
Yeah.
But for the negative one, there's still going to be some field lines that are not captured, that are going to be coming in radially inwards from infinity. That's what happens when you switch it up.
Wait, from infinity? So
You
does
can
that
kind
mean
of
that
think
when
of it
you
like
just
that.
have a lone negative charge,
Mhm.
those radial lines can just be extended to infinity?
Well, it's just an idea. See, if you're out at infinity, that point charge, its electric field is almost zero. Why?
Yeah.
Because
Because it's infinitely far away.
the electric field for a point charge is k q over r squared. It's a radial field, right? So as soon as you start moving away from the charge, this r squared makes sure that the charge's electric field is pretty close to zero
Oh, wow,
when
it's
you're really
another
far.
inverse square law.
It's another inverse square law. Light follows an inverse square law, gravity follows an inverse square law, and electromagnetism
How
follows an
come it all
electric square law.
follows an inverse square?
Not everything follows an inverse square law, however, and we'll see that in the future. Anyway, so this is the idea of an electric monopole. Now, let's consider some things that may or may not matter when it comes to electric monopoles. Does the individual charge matter? And we're going to consider these after we zoom out. So the whole idea of a monopole is, imagine this. Imagine you have a car that's driving on the road. So you have a car that's driving on the road. Here's a car. Very nice car. And
Bro, that is one disgusting car. How are you gonna fit in there?
and you're
Where's the
looking.
windshield in the back window?
Yeah. This is a car for smart
Look at
people.
that stick man. That is cursed.
So you're looking at this car, and this car is arriving at you, right? This car is
That car should crash into that thing.
now at first you're very far away from the car. So let's say you're over here, okay?
Uh-huh.
Let's say there are some headlights on the car, right?
This Uber sucks.
If the car is really far away, how many headlights will you see?
Wait, how does this relate to what we were?
You'll see very shortly.
We will only
So-
see a few because only a few of the light rays are directly.
Yeah, you'll just see
pointed
one headlight, right? You'll just see one beam of light that's hitting your eyes.
at. Yeah, because all the others
Right.
are too far away from you.
They're too far. But now, as the car starts approaching closer, what's going to happen?
Then more of those light rays start hitting your eyes.
What used to look like one headlight now starts looking like two. And then as the car gets closer and closer, what looked like two headlights are actually four. So, what we're going to do is see very far away that those four headlights look like two headlights, and then those two headlights look like one headlight, right?
Mm-hmm.
Well, what we're going to do in this situation is we're going to zoom out. Just like looking at the car from very far, we're going to take a really bird's eye view, no pun intended, of this electric charge distribution. So let's do that.
I'm kind of getting tired.
It's okay. So let's zoom out here.
Can this be the last part?
Sure. So let's zoom out and let's see what happens. So we zoom out all the way, and I want you to notice something. When you zoom out of this electric charge configuration, like before we saw, okay, there's a plus 5 Q and there's a minus 3 Q, right? We
Yeah.
saw them close together. We saw that the electric field lines were like this. Some of the positive field lines went outwards. And you asked the really nice question, what if there was more negative than positive? Well, then there would be more, there would be a few field lines going radially inwards that are not paired up, right? Just like this, but they would be going inwards.
Yeah, that's cool.
Now, what if we zoomed out really far? Well, it would look like, what do you think? What would happen if we zoomed out really far?
They would look like little points.
Little points, right? So,
Oh, is that where point charges come from?
yeah,
There's, like,
basically, yeah,
point masses?
right. So, initially, at a normal distance, this is how the two charges look like. Here was your plus 5 and here was your minus 3. But then you zoom out and they start looking smaller and then smaller still. And then at some point it looks like you're looking at literally one charge.
Oh my god!
Just like
I just realized.
a car
The distance between
going farther
them.
and farther.
Yeah,
Right.
the distance between them kind of gets smaller as you.
Exactly. And in fact, what happens is when you go really far,
don't think you'll need it to add in that many reallys. Please edit that out.
this 5 charge and negative 3 charge just looks like a plus 2 charge. What do you know? Why do you think that is? Why? Where did we get 2 from?
5 minus 3.
Brilliant. That's right. It didn't have to be this way. Nature didn't have to be this way. It could have been
I think
5.
It does have to.
It could have been 5 times 3, could have been 15. It didn't have to be this way, but it worked out this way. Why did it work out this way? Well, look at the
Because
field
when you
lines.
combine two numbers, you get their sum.
No, not necessarily.
Yeah.
Especially in mods. But why did this happen? Because think about the field lines. This guy throws out 50, this guy sucks up 30. So only
That's
20
only
field lines are left, equivalent to a plus 2 charge. So when you look out really far away, it just looks like a plus 2 charge.
No
You don't
way.
know that there's a plus 5 and a minus 3. You're just like, oh, okay, there's just a
So you
plus 2
basically
charge.
only see the net charge.
The net charge, that's the big idea for electric monopoles. Electric monopoles are like communism. This is a controversial idea, but communism. Why? Because it doesn't matter what your individual charge is. I don't care you're a plus 5. I don't care you're a minus 3.
It's just the net sum.
It's just the net charge that matters. Exactly. In communism, do I care about each individual? No. I care about the general output. I don't know remember much of AP Euro, but that's the one thing I remember. So, does individualism matter?
Imagine taking AP Euro. Seems like hell.
No, individualism does not matter. What do I mean? Each individual charge doesn't matter. What matters? Hit it?
The net charge.
The net charge matters. I don't care you're a +5. I don't care you're a -3. I care about the total sum, which is +2. But there's more. What if
No way, man.
What if I did this? What if I switched them around? What if I put the -3 here and the +5 here?
It would still look like +2 because addition is commutative, right?
I mean, it would still look like +2 from far away, but because there's a deeper reason. There's a deeper reason. What if I put the +5 like literally on top of the -3?
It would still work because the distance between them still gets smaller, right?
It still gets smaller, but there's a deeper reason why that happened. It's because as you go out really, really far away, I said it looked like a +2 charge, right?
Yeah.
And what do the field lines for +2 charge look like?
Only like a few dispersed ones.
Well, describe it?
Like.
Use radial. They would be radial, and they would be pointing outwards or inwards? Outwards, right. So they would be pointing radially outwards. So,
Why did you draw that many field lines for +2?
just to demonstrate. Anyway, so it doesn't matter what orientation the charge distribution is in, because the field lines are radial when you're very far away. Radial, so it has radial symmetry. That's why it doesn't matter. That's why the orientation of the electric charges don't matter, because you have radial field lines, you have symmetry. So what that does is it hides the orientation. I don't care your +5 is on top of your -3. I just care that the net charge is +2. And because the net charge is +2, the field lines are radially outwards, and it seems like we've just put a student to sleep. Now, so the individual charge doesn't matter, the orientation doesn't matter, but let me ask you something. Are you ready for this?
Yeah.
Are you ready for this?
Yeah.
Does the charge separation matter?
It's 1 a.m. Please help.
Does the charge... Let's say the distance between these two charges is d. Does that distance matter?
Separation.
Does the distance between the two charges matter? Take a guess.
No.
Come on! It does not matter. Why?
Because if you zoom out really far away, it all looks the same. Like
Exactly.
You can limit to infinity.
Exactly. It doesn't matter, because at the end of the day, you're really far. You're really far. So it doesn't matter what the distance between the two charges is. But now, allow me to ask you one question. Are you ready? What if we now made this -3 a -5 instead? Take a guess. Take a guess.
You murdered my bird.
No
And
birds.
now you're asking me to take a fucking guess.
This is a video.
Sorry. What were you saying?
Now, instead of a -3, let's make it a -5 charge. Okay? What do you think would happen?
You wouldn't see nothing.
What do you mean? Take a guess.
Because it would be a sum of +0 charge.
Okay, before
So
we
because-
move on to the dipole. When we had a -3 charge, when we had a +5 and a -3, did the individual charge matter?
No.
No, why?
Because, no matter, because you're basically only looking for the net charge once you zoom out.
Exactly.
Because the distance between the charges, once you zoom out.
Exactly. Does the orientation matter?
No.
Why?
Because the radial lines point in every single direction.
Because of radial symmetry. It masks the orientation of the electric configuration. And does the charge separation matter?
No, because even if you zoom out really, no matter how far they are, if you zoom out really far away, you will always see them close together.
Exactly. Now this is for the electric monopole, right? Mm-hmm. How do we calculate the electric monopole? Well, what matters? Does the individual charge matter?
No.
What matters?
Net.
The net charge. So the electric monopole, the monopole is simply the net charge, which is the integral of the volume charge density over the volume of whatever space you're considering. So just integrate your volume charge density and you'll get your electric monopole. Now let's talk about the electric dipole. Okay, so
No, please.
how can I make this a dipole? Right, so we've seen how we can get the formula. Why? The electric dipole moment is Q times D. But what about the electric field just the dipole moment? I mean, this is just the dipole moment. Why does it matter? At the end of the day, we just care about the electric field, right? The electrostatic field. So let's talk about it. Let's say we have a plus charge here and a minus charge here. And we want to calculate the electric field due to the dipole on the axis of the dipole. So let's say we make these lines instead of dashed. Let's make it a straight line. Let's say I'm really far away, as you do, as when you calculate the dipole moment, you assume that you're really far away from the charge distribution. That's the whole point, right? You don't have to find the potential in a difficult way. You can just find the dipole moment real fast and easy. It's a quick and dirty tool, right? So let's say we want to find the electric field right here. Okay, and let's say that the distance, the charge separation right here is D. And the distance between where I am and where the charges are is this vector r. In fact, I don't even have to use a vector because we're doing it in one dimensions, right? So we of course know that the field lines for an electric dipole look something like this, right? And of course the whole point of a dipole is that all the electric field lines get captured. So you've got even the backward field lines get captured, sort of like this. It's really, really cool. So this is the electric dipole, and we just want to find the electric field along the axis of the dipole. Really far away, but on the axis. So electric field, that's not how the electric field looks like. The electric field on the axis of the dipole. So let's talk about it. Well, on the axis of the dipole, what is the electric field? Let's think. The electric field for a point charge is 1 over 4 pi epsilon naught, K in other words, Q over R squared. Well, here what do we have? Here we have one charge that is negative, so that's going to create an electric field line going this way. One charge that's positive but farther away, so it'll be weaker, and that'll create a field line that's going outwards. So we expect the net field to be, well, less than that, but less than the electric field due to just the negative charge. But we expect the net electric field to be in the negative direction, in the left x direction. Okay, so the electric field due to this guy is going to be what? Due to this negative charge, the electric field is going to be 1 over 4 pi epsilon naught K Q, but of course it's a negative charge, over R squared. And due to this positive charge, the electric field is going to be E plus is 1 over 4 pi epsilon naught Q over R plus D squared. Okay, and of course I want to find the net electric field due to the principle of superposition. I can simply add them up to find the net electric field. So the net electric field, I should put vectors here, but of course they're all just in the x direction, so I'm putting the I hat vector. So the net electric field is going to be 1 over 4 pi epsilon naught. Let's put my Q where it belongs, right there. And I'm going to have minus 1 over R squared and plus 1 over R plus D whole squared. Well, at this point, I'm going to go ahead and put common denominators for this guy. So let's, over here, hopefully you can still see this, but all I'm going to do is put common denominators. So let's bring it right here. So the electric field is going to be Q over 4 pi epsilon naught, and I'm going to have minus, we'll have R plus D squared over R squared plus, actually, not over R squared. The whole point of common denominators is that this become R squared plus times R plus D squared plus R squared over R squared R plus D squared. So let's simplify this. What are we going to have? Well, let's expand this out. I'm going to have, of course, I'll have my Q over here, Q over 4 pi epsilon naught. Forgive me if I'm not writing my vectors. This should be in the I hat direction. So I'll have minus r plus d whole squared is r squared plus 2rd plus d squared all over r squared times r plus d whole squared. So r squared times r plus d whole squared. And then we're going to add to this r squared over r squared plus r plus d squared. Now notice something. This minus sign can be a bit deceiving, but it's multiplying this entire fraction, right? So really what we have here is minus r squared minus 2rd and minus d squared, right? And what do you notice? Well, minus r squared and plus r squared, they happen to cancel out. And so what are we left with? Well, let me write this over here on the top. We're left with the electric field, the net electric field in the I-hat direction is going to be q over 4 pi epsilon naught times all of this. So let's write that down. Let's write all of that down. We have minus 2rd minus d squared over r squared times r plus d squared. Okay, well, what do you notice at this point? Well, what I see is that I can factor out a d, but that doesn't really help. What's going to help is the following. Since I have r much greater than d, in other words, since I'm really far away from the charge distribution, so that the distance, the charge separation between the two charges doesn't really matter, it's negligible. I'm really far from the charge, so the charge separation doesn't really matter. In other words, my position from the charges, from the charge distribution, is much greater than the charge separation distance. So I can make the following approximation. The electric field is going to be I hat q over 4 pi epsilon naught. And now instead of r plus d, since r is much greater than d, I can just write it as r squared, right? R plus d just becomes r, and so I have r squared times r squared gives me r to the 4th on the denominator. And on the numerator, I have minus 2rd minus d squared. All right. So how about we do something right here? So I'm going to divide both of these by r to the 4th. So let's break up this fraction into minus 2rd plus minus d squared over r to the 4th. But of course, when you're really far away from the charge distribution, when r is much greater than d, this is close to 0, right? So what are we left with? We're left with the following equation. Q times minus 2rd over 4 pi epsilon naught times r to the 4th. R divided by r to the 4th leaves us with the power of r cubed on the denominator. So the electric field on the axis of the dipole is going to be q over 4 pi epsilon naught times minus 2d times minus 2d over r cubed. Wow, so we see a lot of things popping up here. But before I explain them, let me just write out the answer a little bit more nicely. So I'm going to have minus 2qd over 4 pi epsilon naught r cubed in the I hat direction. And of course, this is my dipole moment right here. So if you want, you can write it like this, minus 2p 4 pi epsilon naught r cubed. And I should have mentioned the dipole moment always goes from the negative charge to the positive charge. And so this minus is actually going to be incorporated into the dipole moment right there. So since it's going in the minus direction. So this is the electric field on the axis of a dipole. You can learn a lot just by looking at this, right? Notice that the electric field is going down as a cubic, not as an inverse square, but as an inverse cube. Why does that matter? Well, remember that the electric field for a point charge goes down as 1 over r squared, not 1 over r cubed. So the electric field for an electric dipole decays much faster by a factor of 1 over r than the electric field for a point charge, right? And you can see that if you look at the field lines for an electric dipole, they get much farther out quicker than for a point charge. So I'm going to write all of our results right here on the right hand side, but right now we've just calculated the electric field due to an electric dipole on the axis, and we found that it's 2p, 2 times the dipole moment over 4 pi epsilon naught r cubed. Now let's find the electric field due to a dipole on the equatorial line, equator of a dipole, on the vertical line that is the axis of symmetry between the plus charge and the minus charge. Let's do it. folks, so I'm going to be writing down all the properties of dipoles that we derive on this side of the board. We've just found out that the electric field due to a dipole on the axis of the dipole is 2 times the dipole moment, so it's in the direction of the dipole moment, but it decays as an inverse cube, not an inverse square, as for a point charge. And we also derive something else, not really derive, but we experimentally figured out that the dipole moment is proportional to the individual charge, and it also cares about the orientation and the charge separation between the two charges. So let's write down all the information we discover about dipoles right there, okay? So dipole moment and the electric field due to a dipole on its axis. Now let's find the electric field due to a dipole not on its axis but on its equatorial plane, which is this, which is just that. Again, the charge separation is going to be described by this factor, by this variable d. And now let's say I want to find the dipole moment really far away. So really far away on this equator. So here is the equatorial line for the dipole, and I want to find the electric dipole moment somewhere here. Now when I first thought about this, I thought, wait, the electric field over here should be 0, right? There's a plus charge and a minus charge. They have the same magnitude of charge, like +1 and -1, and I want to find the electric field at a point that's equidistant to both charges. So shouldn't the electric field be 0 there? But before we make any hasty assumptions, look at where the electric field lines are going. For the plus charge, the electric I guess I gotta draw it a little lower, because I've got to draw the vectors, so I gotta leave myself some space. But for the plus charge, I'm going to have a vector that's going outwards, right? That's going to be the electric field line due to the plus charge. But the minus charge is going to be pulling this way, right? That's the electric field line to the minus charge. And so the net field line, right, the vertical components cancel. Here's your net electric field, right? So that's what we want to figure out, the net electric field. And it turns out it's not 0. It's not 0. Because even though the vertical components of the electric fields cancel, the horizontal components add up. They add up. And so let's find what that is. Let's call this theta. Let's call that angle theta. And let's say that we're a distance r away from each charge. Okay, so let's find the dipole moment. So on the equator. So the electric field on the equator is going to be what? Well, first notice that this theta is going to be the same as this theta. Why? Well, just draw it out. You'll see that if you have a triangle like this and you keep going in the direction of that hypotenuse and you draw the horizontal, notice that these two angles should be the same. That's all I'm saying here. These two angles are the same. Why does that matter? That matters because that means the net electric field is simply going to be adding up these horizontal components, right? And what are the horizontal components of these two guys? Well, it's simply going to be E cosine theta. But since I'm adding them up and their horizontal components are equal, since I'm equidistant from both charges and both charges have the same magnitude, I'm simply going to have 2E cosine theta. Well, what is E? What is E? Well, E is the field due to one charge. So let's write it out. 2Q over 4 pi epsilon naught R squared cosine theta. But what's cosine theta? Well, notice cosine theta is adjacent over hypotenuse. Adjacent being, well, this, what is that? That's half the charge separation, d over 2. So cosine theta can simply be written as adjacent over hypotenuse, or 2d over 2r. So I'm going to write this as 2q over 4 pi epsilon naught r squared d over 2r. Well, notice what we have here then. This 2 and this 2 cancel out, so we're left with the electric field, which notice is in the dipole moment is in this direction, right? From minus to plus charge. But the electric field is this direction. It's in the opposite of the dipole. So we're going to have QD over 4 pi epsilon naught r cubed. Again, we have an inverse cube field, but this time it's in the opposite direction of the dipole moment. Actually, if your x-axis is in the plus direction like that, then I should keep this positive and just make it negative when I introduce the dipole. So that's the electric field on the equator of our dipole. And so I'm going to write this down right here. the electric field of the dipole on the equator is going to be not 2p but minus p over 4, because this is p, this is the dipole moment, right? QD, that's what we have right there. 4 pi epsilon naught r cubed. 4 pi epsilon naught r cubed. So again, notice that it's an inverse cube field, but now it's in the opposite direction of the dipole, right? So now, can we kind of conjecture what the total electric field of the dipole is at any location in space? Indeed we can, and I'm going to show you that right now. So we have our plus charge and our minus charge, and the plus charge goes to the minus charge just like this, and every field line is captured. That's the whole idea of a dipole, right? No field line is left behind. Every field line from the plus charge that's thrown out is eventually captured by the negative charge. That's the electric dipole. Now, we have found out that the electric dipole moment on the axis, the electric field due to the dipole on the axis is going to be in the direction of the dipole. So if you're measuring right here, the direction of the dipole is this. This is the direction P, and here is the direction of the electric field due to the dipole on the axis. But the electric field due to the dipole on the equator is not along the direction of the dipole. In fact, it's in the opposite direction. It's in this direction. Here's the direction of the electric field of the dipole on the equator. This is on the axis. And so what do you notice? First of all, the electric field on the axis is much stronger by a factor of 2, in fact, right? Here you have 2p, here you have just p. So the electric field over here is much stronger than the electric field here, right? Because by the time you're here, most of the field lines are already captured, right? So if I draw out more of these field lines, maybe that will give you a sense of what the pattern is for the electric field. And now you can actually see why the field lines are in the opposite direction of the dipole moment and then curving back to the dipole moment right here. And actually that's why the dipole moment goes from minus to plus. Because look, imagine you're following along right here. It's going out, thrown out. You've got a field line thrown out of a positive charge. Right here we've calculated, we've shown that the electric field is in the opposite direction of the dipole moment when you're on the equator. You keep going, follow the field lines, and you we calculated that the electric field of the dipole on the axis is opposite to the direction of the dipole, and that exactly agrees with our intuition. And then if you keep going, you'll see that that's why the dipole moment goes from minus to plus, because you're just kind of tracing out the electric field line. That's the idea. And now notice this. What if we wanted to find the electric field at an arbitrary position anywhere in this electric field? What if I wanted to find the electric field here, for instance? Well, I would suspect it would be some combination of this and this, right? In fact, I would dare conjecture that the electric field at any point in the charge distribution is going to be some linear combination of this, the electric fields of the dipole on the axis, which is 2 times the dipole moment over 4 pi epsilon naught r cubed, times something. Now as I go, let's introduce two variables, r and theta, that are going to help me kind of calibrate how I'm going to combine these two. So theta is just going to be this angle from here to here. Okay, it's just going to be the angle as I move up. So now as I move up in this polar kind of angle, which electric field is going to increase? Well, certainly this guy is going to decrease, right? And what do I know decreases as theta increases? Cosine. So I'm going to assign the electric field due to the dipole on the axis to cosine theta, and the electric field due to the dipole on the equator to sine theta, so that it increases as you go up. 4 pi epsilon naught r cubed sine theta. And just add in your unit direction vectors, and voila, you have the electric field in an arbitrary position due to the electric dipole. Alright, so we've just discovered something else. Now we have the electric field in an arbitrary position due to the dipole, which is going to be the electric field due to the dipole along the axis and the electric field due to the dipole along the equator. So the electric field anywhere due to the dipole is simply going to be a linear combination of the electric field due to the dipole on the axis and along the equator, which is what we've just got here. Voila. So let's go ahead and write it down. 2 times the dipole moment. Now this guy is going to be pretty long, but we can do it. Times 4 pi epsilon naught r cubed cosine theta in the r hat unit vector direction plus p hat over 4 pi epsilon naught r cubed sine theta in the theta hat direction. And again, we've talked about why we've assigned cosine theta to this one and sine theta to this one. This right here is the electric field due to the dipole along the axis. I know it's the axis because it's twice as strong as the electric field due to the don't include the sine theta, right? Just this. This is the electric field due to the dipole along the equator. And all we've done is take a linear combination of them. As my theta is increasing, I want my equatorial electric field to increase as well, and my axial electric field to die out. Hence, sine theta for this term and cosine theta for this term. All that this cosine theta and sine theta are doing, they're just controlling knobs, right? As I increase my theta, this one is just ramping up the electric field due to the dipole along the equator, and this cosine theta is just turning down the electric field due to the dipole along the axis. That's all I'm doing. I'm just turning knobs here. That's all this cosine theta and sine theta are doing. Now that we have found out the dipole moment, the electric field due to the dipole moment along the axis, the electric field due to the dipole moment along the equatorial line, the electric field due to the dipole at a general field point, described of course by the 2 coordinate vectors r hat and theta hat. Now that we've done all of that, let's talk about the electric potential due to the dipole. How can we do that? Quite simple. Let's figure it out. Now let's talk about how to find the electric potential due to a dipole. So let's say you've got your plus charge right here, your minus charge right here, separated by a distance of d. And let's say you want to find the dipole potential really far away. Let's say somewhere here, okay? And the distance from the plus charge to wherever you want to find out your electric potential is r sub plus. And the distance from minus charge to wherever you want to figure it out is r sub minus. And now, here comes the kicker. Here's r sub plus, here's r sub minus, and I'm going to add one more, kind of an auxiliary line, if you will, from the midpoint of my dipole separation to wherever I want to figure out my electric dipole potential. And you'll see why this is important in a second. But anyway, this is the general setup for figuring out the potential due to an electric dipole. Okay, so what can we do at this point? Well, let's just write down the potential. The electric potential for a point charge is k, 1 over 4 pi epsilon naught, q over r. So, in this case, we have 2 charges. Hence, we're going to have q first for the positive charge, and then here's for the minus charge. Let's factor out that q. So I've just got an expression in terms of 1 over the distance to the plus charge minus 1 over the distance to the minus charge. Now, remember that we're really far away from the electric dipole. In other words, the distance from wherever we are to where we want to find the distance from wherever we want to find the electric dipole potential is much greater than the electric dipole charge separation. So r is much greater than d, in other words. So all of this takes place assuming r is much greater than d. I mean, that's the whole point of electric monopoles and dipoles. They're just approximations, right? The car is really far away from you. You see first one headlight, monopole, two headlights, dipole, four headlights, quadrupole, 8 headlights, octopole, etc., etc. So let's approximate this 1 over r to the sub plus and 1 over r sub minus using this idea. Okay, how can we do that? Well, the whole reason I introduced this auxiliary line and this angle is so I can approximate these distances using a triangle. Look at this triangle we've got right here. I can write the distance to the positive charge, r sub plus, in terms of the law of cosine, in terms of these two other distances. Of course, since this is d and this is at the midpoint, right? This r vector hits at the midpoint. This is going to be d over 2. This distance is d over 2. Hopefully that makes sense, right? This r vector hits you at the midpoint of the charge separation. Since the charge separation is d, the midpoint gives you d over 2 here, d over 2 here. So now we're going to use the law of cosines to express the distance to the positive charge from wherever we are in terms of the half of the charge separation and this r vector right here. Okay, so let's do it. So we're going to have d over 2 squared. Hopefully you remember the law of cosines. It's just c squared is a squared plus b squared minus 2ab cosine theta, where theta is the angle between a and b. In this case, a is this and b is this side. So d over 2 squared plus r squared. Now you might be wondering, why don't I put the vector symbol on top of these guys, on top of these variables? It's just because I'm finding their magnitude. So the magnitude of a vector would be a scalar, so you don't really have to do it. If you really want to, go ahead. No one's stopping you. So minus 2 times d over 2 times r cosine theta. Okay, good. And what about for the negative charge? For the negative charge, we have r sub minus squared is, again, now we want to express this distance. And what is this angle? This angle is pi minus theta, right? 180 minus theta. So we're still using these two. We're now using r and this length, which is still d over 2. But now our angle is supplementary to what it used to be. So r squared minus 2d over 2 r, and cosine of supplementary angle is just going to be what? Minus cosine of the original angle. And minus minus makes a plus. So that's what you've got right there. So in other words, the distance to either the plus or minus charge may be written as d over 2 squared plus r squared. And of course, this 2 and this 2 cancel out for both. And so we're left with minus for the plus distance. So minus plus, this might look strange, but bear with me, minus plus dr cosine theta. Okay, that's what we've got right there. And so now what I'm going to do is, at the end of the day, I want to figure out 1 over r, either for the positive or negative distance. So let's raise both of these to the power of negative 1/2 so that I can get a negative 1 right here. In other words, 1 over r. So I'm going to get r to the negative 1 plus minus is equal to, what do I have here? I have the following, d over 2 whole squared, blah, 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 blah. Now notice that since first thing I'm going to do is factor out this r squared, and you'll see why. R squared, factor that out, I would get d squared over 4r squared plus 1, and then minus plus dr cosine theta. Well, I've already factored out of r, so that extra r is going to go to the denominator. And now I'm raising all of this to the power of negative 1/2. Okay, well, first of all, you notice that we assume that r is much greater than d. So d squared over 4r squared, that's going to be pretty dang close to 0, right? Pretty close to 0. And so what are we going to be left with? We're going to be left with r squared. Remember, we haven't taken this negative half power yet, so let's keep that in mind. R squared plus times 1 minus plus d cosine theta over r. Raising all of this to the negative 1/2. Now, if I raise all of this to the negative 1/2, what do I notice? R squared to the negative 1/2, well, that's just r to the negative 1, right? So let me write it down This is a very busy whiteboard, but let's write it down right here. So I'm going to have r squared to the negative 1/2 is just going to be r to the negative 1 over here, and then multiplied by 1 minus plus d cosine theta over r to the minus 1/2. Now I'm going to use a Taylor approximation, which is that 1 plus or minus whatever n. Well, let me first remind myself what it is, right? 1 plus n to the x is about 1 plus xn to the first order, Taylor approximation, if I remember correctly. So we're going to apply that right here. This is using Taylor series. So we're going to have the distance, either the plus or minus charge to the negative 1 power is r to the negative 1. R, remember, is that vector, that general vector from the origin to wherever you want to calculate the electric dipole potential. Now notice minus plus is going to be multiplied by this minus half, and I'll still be left with d cosine theta over r here. But I've already applied this power, right? 1 plus n to the x, right? N right here is this, and I multiplied it by my exponent, negative 1/2. So that's why I've got that. I've used my Taylor series approximation. And so I'm going to have the distance to either the plus or minus vector raised to the negative 1 power is going to be the distance from the origin to where I want to calculate the dipole potential raised to the negative 1 power. And this minus is going to flip this minus plus into a plus minus d cosine theta over r. And so voila, I'm almost there. So let me go ahead. At the end of the day, I wanted to figure out, remember, I wanted to simplify this potential right here. So let's do it. Now I can write down that the distance to the plus charge, the reciprocal of the distance to the plus charge, is simply r to the minus 1 plus d cosine theta over r. And the distance to the minus charge is simply going to be r to the minus 1 minus d cosine theta over r. So now if I subtract them, in other words, if I do 1 over the distance to the positive charge minus 1 over the distance to the negative charge, if I subtract these two, what am I going to get? Well, let's see. I can factor out that r to the negative 1, right? So I'm going to have 1 over r plus minus 1 over r minus. Remember, I'm simply trying to find this for the whole sake of approximating this guy, approximating the answer to that guy. So I'm going to have 1 plus d cosine theta over r minus all of this, minus 1, and minus minus makes this a plus, d cosine theta over r. Now, what are we going to have? 1 and minus 1 cancel each other out, and so we're left with, what are we left with right here? We're left with the distance, the reciprocal of the difference between the distances to the plus or minus charge is 1 over r times 2d cosine theta over r. Whoops, it should be a bracket. And so I can now finally express the dipole potential in a much nicer way, in a way that depends only on the angle between d and r, and yeah, you'll see very shortly. So let me just write it down first. I have my q over 4 pi epsilon naught. Now I can replace this crap, 1 over r, 1 over the distance to the positive charge minus 1 over the distance to the negative charge. I can replace all of that with this, 2d cosine theta over r squared, r times r. And now if I write this even more nicely, what am I going to get? Well, first of all, there's one thing. All right, folks, it seems like I forgot to apply this 2 to the r. So we're going to have a 2r over here, in fact. And so when you add them up, you get 2d cosine theta over 2r. And so you're just left with d cosine theta over r squared. And so your dipole potential is going to be 1 over 4 pi epsilon naught qd cosine theta over r squared. Well, wait a minute. QD, I've seen that before. That's the dipole moment. That's the magnitude of the dipole moment. And so the dipole potential is simply 1 over 4 pi epsilon naught, the dipole moment. How can I express that cosine theta in a nicer way? Well, I can say that I'm going to take the dot product between the dipole moment and the unit vector in the radial direction, r hat. all divided by r squared. And this is the general equation for the dipole potential. This right there, ladies and gentlemen, is the equation for the electric dipole potential. Wonderful, wonderful. And as you expect, the dipole potential is quadratic because when you find the electric field and you differentiate that quadratic term once more, you get an inverse cubic. And that's exactly what we found for the electric field of a dipole at an arbitrary point. And so we have one more discovery to add to our long list of discoveries for the electric dipole. And that discovery is that the electric potential due to a dipole is nothing more than 1 over 4 pi epsilon naught, that crap constant, times the dipole moment, the dot product with the unit radial vector over r squared. All right. And why was it so important to kind of get rid of that 1 over r plus and 1 over r minus? Well, it's because now we've really expressed the whole thing in terms of stuff we know, right? If you want to calculate the dipole potential some point here, this is r plus, this is r minus, this is r, and here's your dipole, here's the plus charge, here's the minus charge, here's the charge separation d. Now we've really expressed everything in terms of this vector r, how far away you are from the midpoint of the dipole, your origin, if you will, and how and this dipole moment, which goes from the minus charge to the plus charge. So isn't that wonderful? I mean, this is amazing. You've got an expression that lets you calculate the dipole moment solely based on, let's say I have my coordinate origin right here, and my positive charge here, and my negative charge here, positive charge on the y-axis. And I want to calculate my dipole potential here. Well, guess what? Here's the dipole moment, P. Here's the distance to wherever I want to calculate the dipole moment. Let's call that R. And if I take the dot product between P and R cubed, because this is the unit, this is the not normalized vector, r cubed. If I did normalize it, then it would just be r hat, and this would be r squared. But let's say I'm just taking the normal dot product without the unit vector, just for convenience. Then the dipole moment is just this. The dipole electric potential is just this. It's so simple. It's so simple. All you need is the dipole direction and wherever you want to calculate it. I mean, does it get better than that, folks? It does not. It does not. Does it get better than that in life? So these are all the nice, amazing things we figured out about dipoles. But there's still more to figure out. What is the force on a dipole in a non-uniform electric field? What's the torque? What's the electric potential energy of a dipole? More on that on the next calculation. So now let's figure out the torque on an electric dipole in a uniform electric field. So consider a uniform electric field such as this, that is pointing to the positive I hat direction. What if I had a little dipole here pointing like this? Let's say the dipole was oriented at an arbitrary angle. Here's my electric dipole. Here is my electric field. Question is, what's going to happen? Well, this electric field is going to exert a torque on the electric dipole. But isn't it also going to exert force? Well, let's see. This electric field is going to want to align the dipole with the electric field. So what is going to create an electric field like this? Well, you can imagine a kind of positive charge, and the dipole is made out of nothing but no more than a negative and a positive charge. So this positive charge is going to get repelled by that positive charge, and this negative will get attracted. So you've got a force here and a force here, but of course F is QE, and since Q is equal and opposite for these two guys, they're going to cancel out. So the net force is going to be 0. But notice that the two forces are acting to kind of rotate the dipole, right? They're kind of exerting a torque. And in fact, we can summarize this as follows. So let's say we have our coordinate plane right here. And let's say we have our dipole right here. Here's my dipole, P. And what I want to figure out is the formula for the torque of the dipole. So let me call this my minus charge, call this my plus charge, and let's say that this is the distance to the positive charge, distance to the negative charge, and let's say my electric field is once again a uniform field in the I-hat direction. Here's my electric field. And what I want to figure out is the torque exerted by this electric field on the dipole. That's the whole idea of a dipole. A dipole is nothing more than a bike handle that you rotate. The dipole is like a bike handle, and the electric field is like a hand rotating that bike handle to align with the direction of the electric field. So remember that torque T is nothing more than R cross F, where R is your moment arm. The distance from here to here, for example, would be the R for this. So you would have a torque due to the positive charge and a torque due to the negative charge. And of course, torque is a vector. And so what we'd have is, for the positive charge, I would have R, the distance to the positive charge, cross with the force exerted on the positive charge, plus the distance to the negative charge, cross the force exerted on the negative charge. Well, now what do we have? This is the net torque. And notice that, of course, the force exerted on any charge is going to be Q, the magnitude of that charge, times the electric field that that charge is inside. So we're going to have the torque is no more than the distance to the charge crossed with Q E. And this is, of course, E to the uniform fields, plus the distance to the negative charge crossed with minus QE, right? Since we have a negative charge here, the force is going to be in the opposite direction. And now what are we going to have? Well, let me go ahead and jumble things up a little bit. Let me rewrite this as the distance to the positive charge, and then since I have a minus sign here, I'm going to move this minus sign to this negative r hat vector, r vector, not r hat. So I'm going to rewrite my expression as the difference of the distances between the from the origin to the plus vector and to the plus charge, and the origin to the minus charge, and that's going to be crossed with QE. Well, look at what I have here. What is the what is r plus minus r minus? Well, that's this distance, right? R plus is this, r minus is this. Subtracting them gives me this distance right here, the distance between my two charges, aka the charge separation. So the torque is going to be no more than this, which is just the charge separation d, which is a vector, right? So I'm going to have d crossed into QE. Let me move this q over here. Since it's a scalar, I can move it around between vectors. QD crossed with the electric field. Well, what is QD? QD is nothing more than the dipole moment, P. So P crossed into E. Well, ladies and gentlemen, I think we have the torque exerted by uniform electric field on a dipole. So let's write that down. Let's write that down. Yet another accomplishment, another discovery to add to our results. The torque, which I will write nicely as N hat, is going to be P dipole moment crossed into your electric field. And in a uniform electric field, of course, there will be no net force on our electric dipole. So now you might wonder, okay, but what makes this formula valid? Can you give me some intuition for this formula? And the answer is yes. Yes, I can. So let's take a look at some examples. Let's say your uniform dipole, your uniform electric field is pointing this way, and your dipole moment is pointing this way. Well, I would conjecture, my intuition would say that if the dipole moment is perpendicular to the electric field, that's when the torque should be at a maximum, right? Well, what's the angle between these two guys? The angle certainly looks like it's 90 degrees. And the cross product, if I take P crossed into E, which can also be written as P sine theta, sine of 90, well, that's when sine is at a maximum, when you're at 90. So this is going to be at a maximum. The torque is going to be at a maximum when the electric dipole is perpendicular to the uniform electric field. On the other hand, if your electric dipole is already pointing in the direction of the electric field, then there's no torque, right? Because now the two directions are parallel. They're parallel. So the angle theta is simply going to be 0. The angle theta is going to be 0. So and sine of 0 is 0, so there's no torque. So that hopefully that gives you some intuition for the torque on an electric dipole in a uniform electric field. Here the torque is maximum, gets smaller, 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 and now it's 0. Although due to momentum, the dipole may keep on going like this and then finally slowly align with the electric field. So that is the equation for the torque exerted on an electric dipole by a uniform electric field. Now let's talk a little bit about the force exerted on an electric dipole. In a uniform field, there will be no net force, right? The forces are equal and opposite. They're going to cancel each other out. F here, F in the opposite direction, they're going to cancel each other out. The direction is indicated by this arrow, so I don't need a minus sign there. But what if you have a non-uniform field? Well, for non-uniform fields, I'm going to give you an intuition for the formula, but not exactly derive the formula. So the formula for the electric force, just the force on an electric dipole in a non-uniform field, is going to be the force is equal to dipole moment. It's going to look kind of strange, but just bear with me. Dotted into nabla times the electric field. So it's a vector. You can check it yourself that is indeed a vector. But how do we get that? What's the idea behind that? The idea is simply this. If you have, let's say, we have a non-uniform electric field here. So for example, instead of this, I'm going to draw a picture where I have a small point charge at the origin, and I have my little dipole pointing up here. So here's my dipole moment, and here's a point charge. And my dipole moment, as you can see, in this case is oriented in the j hat direction. So in this case, I'm going to have, let's say this is the plus charge, this is the plus part of my dipole, and let's say this is the minus part of my dipole. And so what I'm going to have is, this is a plus positive charge here, so that's going to repel this guy and attract this guy. And so there's going to be a torque twisting the dipole to align with the electric field. But since here I have a non-uniform electric field, I'm going to have to calculate the electric force, right? It's going to be non-zero. The electric force in this case is going to be dipole moment times how much the electric field changes over this distance, right? First you're going to have the electric field over here, and then you're going to have the electric field over here, right? In other words, you're going to have F is equal to QE over here, and F is equal to QE over here. And E is going to change between the plus and minus because this is a point charge, right? It's going to have different fields throughout the coordinate space, even though it has radial symmetry. And so that's the idea. We want to see how much the electric field changes over a certain distance. And so that's basically how you can get the force exerted on an electric dipole. That's what this formula is really saying. It's just saying, all right, tell me how much the electric field changes, and I'll tell you the force on the dipole as a result. And you have to evaluate this at x equals, let's say, a, y equals 0, z equals 0, of course. So, ladies and gentlemen, that is it for today's lecture of electric dipoles. We have calculated the dipole moment, the electric field due to a dipole on the axis, the electric field due to the dipole on an equator, the electric field due to a dipole in a general field point, using the radial unit vector and the theta, the polar vector theta. We have found the electric potential of a dipole. We have found the torque exerted by a uniform electric field on an electric dipole, and we have found the force on an electric dipole. The last remaining thing that I would like to leave this lecture with is the energy of a dipole in an electric field is the dot product of the dipole moment with the electric field, so that that energy is maximum when the dipole moment is aligned with the field, and minimum when it's perpendicular. Well, folks, thank you for watching this episode of electric dipoles. We'll see you in the next episode.